studying for biology.
All right, so we'll go ahead and get started. Today we're really going to go over bubble sort and bubble sort and binary search. But before we go into that, I think we should at least talk about recursion. Hopefully you've touched base on recursion a little bit. It's actually a very extremely powerful tool. What do you all remember about recursion?
It's a function calling itself.
Function calling itself, correct. So we're going to go over recursion a little bit. Do y'all remember this? Kind of rusty?
Didn't know OP a little bit.
Didn't know OP a little bit, but not too much. There are a lot of data structures that have very nice recursive solutions, especially when we get into binary trees. Some of them are really easy to write recursively and really annoying to write iteratively, aka with a loop. So it's important we actually cover recursion. I'm going to cover in a little more depth here, and then we'll jump over to our actual topic of binary search, which hopefully you can see that if you use recursion for that, it'll be easy. You can still do it iteratively, just the recursive way is a little simpler. All right, this is what chapter is this? 15 in your book. That's great. Solving a problem by reducing it to smaller versions of itself. All right, yes. Or when a function calls itself. So hopefully y'all have done this in, discrete structures, the math class? Have y'all been taking that?
Yeah.
You've taken that? So this is where you've done induction, where you had your base case, and then you basically...
You prove the first case and then you work the next.
Right, so when you do recursive definitions, you want to follow the exact same methodology. You want to define your base case first, because the base case will tell you when you need to stop, and then you define basically what you want to do for every other iteration besides the base case. If you stick to this method, your recursion will work nicely and it'll be easy. If you try and do your base case somewhere that's not on the top of your function, only sadness will occur. Trust me. Now you can do it. I've seen it happen. People can pull it off. But I have yet to meet someone who thinks it's easier to not put the base case on top. And let's go jump over to code just so we all can see what we're doing here. Go ahead and load up a quick window. Let's jump over to CSU courses, csci 315, class code. We'll make a directory called recursion. That sounds great. Recursion, and we'll go open up main.cpp. Go ahead and include iostream, int main, int arg c char arg v. All right. So we'll reopen that up, return 0. And let's go ahead and open up a new tab, g++, main.cpp, main, good, compiles. Let's compile and run it. Beautiful. Okay. So I'm going to do a really basic example right now. We want to just print all the elements inside of an array. So to do that, I'm going to go ahead and just create the array first. So int, I'm going to call it I array equals, I don't know. Come on, give me some numbers.
72.
12, 44?
Yeah.
18.
18? 19? 20? 21. All right, how many elements is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, 9 elements. Great, so if we want to print this, normally what we do, and what I would recommend doing, is we would have a for loop, right? Int I equals 0, I is less than, what do we say, have any word?
9.
9, thank you. 9, I++, and then you just have, you print it out. We'll put a comma right there. And then when we're done, we'll do, oops, let me make sure those are together, the \n. And this is generally how I would recommend you printing it out, but since I'm trying to teach you recursion, I'm going to show you how you can change the simple for loop into a recursive definition just to get the idea of recursion into your head, and then later we'll go into hopefully some situations where the recursive version is a lot simpler. So I'm going to go up here. It's a function, so we're going to have void. I'm just going to call it recursive print, and it's going to be passed in the array. And then we'll have, let's see. We're going to print it, I guess, in the forward direction. So we'll have position, and then we'll have to also know size. Okay? So this is the actual data array, where we are in printing it, and the size of we want to print. So the idea is that when we call this function, we're going to do recursive print on the array, starting at 0, and then going to size, which is 9. So we want to print from index 0 all the way up to 9. Everyone following me so far? All right. So the first question is, we have always write your base case on top. Yes, I know I'm using all caps, which means I'm shouting. Yes, I am shouting. Because if you don't write your base case first, you will be very, very sad. So please, please always write, actually an S on there, your base case first, or only sadness will occur. I'm going to tell you that over and over again. Oh, that was cool. Over and over again until we get this right. All right, so what would be the base case here? When do we know to stop printing? Well, we haven't quite figured out the recursive print, but the base case would be once our position is equal to the size, we're done printing, is what our base case is going to be. So if position equals the size, we're done. And if you noticed up here, when we were done, we printed a \n. So I'm just going to go and put that code in there, and then I'm going to put in return to signify to exit this function, and we're no longer needing to recurse. Otherwise, what are we doing? Well, inside this for loop, we're going to print off the value. So let's go and print off iri sub position. And then we're going to recurse. So usually after the base case, you want to do the work, and then lastly, you want to recurse. And this is simple tail recursion. So you do recursive print on the I array, and you want to increment the position because now we've printed off at position, so now we want to go to position +1, and we still want to keep track of whatever size is. Okay. Have any questions about this example? Go ahead and make sure I did that correctly. Notice it printed off the same thing. How many times was the recursive print function called? That's going to be a good one.
Is it 8?
That's more than 8 because it printed off 9 numbers.
Oh.
So at least had to be called 9 times, right?
10.
10, right? Yeah. Other +1 because there's a final recursive call where it found out it was done and then it exited. Okay. So, base case on. All right. Do you all see what's going on here? And hopefully, in my previous class, I made it very obvious. Every time a function was called, it made a completely new copies of all your local variables on the stack, did everything. So there's actually 10 copies of this recursive print on the stack while it's being called. And yes, recursion uses the internal stack of your computer, which behaves the exact same way as the stack data type that we talked about last class. They're both actually the same, just in our other stack, we made it explicit where you push and pop. This one's using the computer. You okay, Matt?
Yeah, I just like it just makes sense. It's the same thing.
It is the exact same thing. All right. Okay, good. So we talked about the base case in which the solution has been obtained, aka we've finished printing everything. Every recursive definition must have one or more base cases. You can have more than one base cases. Again, make sure all your base cases are on top or sadness will occur. Because it's what stops the recursion. If you don't put your base cases, it may not stop your recursion because you may accidentally if you put the base cases after your recursive calls, you may just go into, well, what would happen actually?
Infinite recursion.
infinite
Well,
recursion.
Well, until a memory error.
Well, it may be a memory error, or well, yeah, it'd be a memory error. You're going to blow your stack, right?
Yeah.
Your stack can only get so big. So yeah, in actuality, you run out of memory first. Although the theoretical terminology is infinite recursion. It is best to keep in mind that in your general case, you must eventually reduce to some sort of base case in your calculation. All right, so another one. Okay, good. Factorials. 0 factorial is 1. Otherwise, you must go ahead and do the multiplication. Hey, Jonah. Recursion, right? You got this?
Mm-hmm.
Good. Perfect. What's nice about recursion is a lot of mathematical formulas become really easy to code because they're going to be written like this, and then you can just go factor them in. So we're going to go ahead and do the factorial int n. And so if we want to know what factorial of 5 is, and we'll want to print that out, actually. Actually, it's the symbols like this, equals. Yeah. I'll go ahead and start this int factorial int n. All right. So I'm going to start the definition here. What do we need to write first?
Base case.
The base case. What is the base case?
N is greater than 0.
When n is 1.
When n
Is 0. When n is 0, so base case, if n equals 0, we return, what are we going to return? 1. Perfect. Otherwise, what are we doing? We're multiplying. What are we multiplying?
N times n minus 1.
Not n minus, not quite, yeah, it's definitely n times, now it's not n minus 1, it's actually,
N minus 1 factorial.
there we go, yeah, times factorial of n minus 1. Now this function is returning, so we want to actually return it. Wow, that was easy. Let's see if we did that right. Looking good. I don't know if 10 factorial actually fits an integer, but we'll find out. I think it does. Yeah, I'm pretty sure it does. Good. All right. You see how easy that was? Very simple. All right, so the book calls it a recursive algorithm finds a solution by reducing the problem to smaller versions of itself. A lot of times this is called divide and conquer. And you will, there are many times where it's just easier to write things recursively than it is to write them iteratively. When I say iteratively, I'm talking about using loops instead of functions. Here's a good question. Which is more powerful, a loop or looping or using recursion? You think recursion? Any others? You said loop. You
I
said
would
loop?
say recursion.
They've been proven that they're the same.
True.
Come on, Jonah.
No.
Yeah, it depends. Or, yeah,
Depends.
Okay. So yeah, I know I was being a little snide there. I know, I understand. But yeah, I want you to understand that they're actually equally powerful when it comes down to it. Anything you write recursively, you can write iteratively. Anything you can write iteratively, you can write cursively. Really, it's just which one's going to be easier to write depends on the problem at hand. It depends. Which one should you choose? It depends. Perfect. All right, so recursive algorithm, that's the theoretical idea of how you're solving a problem. Basically reduces it to smaller versions of itself. If you've done discrete structures, it's induction is really what's going on. recursive function is just simply a function that calls itself. So you're doing a recursive algorithm by writing a function that calls itself to reduce it into smaller pieces. And that is what's happening here. Factorial. You have your base case, but factorial of n, well, it's n times, and let's go ahead and get the factorial of what's smaller than me. So you've already done the part of n multiplied by something. Let's go do the next part of factorial minus what? N minus 1. Let's see. Think of recursion as having infinite many copies of itself. Every call has its own code and set of parameters and local variables. That should be very obvious from what I've talked about earlier with memory. Every time you call a function, you're allocating all the local memory on the stack every time the function is called. All right. There's directly recursive and indirectly recursion. I highly recommend you never do indirectly recursion. It'll be sadness will occur. Direct recursion is what we've done so far. The function directly calls itself. Indirect recursion is when a function calls another function that eventually results in calling the original function. So like A calls B, B calls C, C calls A, which calls B, which calls C, which calls A, and you have that loop. But the recursive definition isn't defined within the function itself. You want to, why do you think indirect recursion is not?
Sounds like a mess.
It is a mess. It's a mess.
I don't think you have to worry about us doing that.
He's seen it all.
Thank you, Matt. I've seen it all. It's going to happen. Please try not to do it. Tail recursion. This is a nice version of direct recursion. You do not have to do tail recursion. Some algorithms you can't, and that's fine. But tail recursion is nice because the recursive call is the last statement executed, and it does make your recursion very easy to read. And that's what we've done so far, because the recursive call is at the very end here, and the recursive call, again, is at the very end. So that's what I've done so far is tail recursion, which is a nice form of direct recursion. Let's see, infinite recursion, every recursive call results in another call, so it's kind of like, in theory, infinite recursion executes forever, right? But your memory is finite, so eventually it's going to run out of memory and give you an error. All right, designing. Basically, really, when you approach a problem, think about how you wish to solve it. If it really helps to just break it down into individual pieces that are nicely divided out, recursion might be a good solution. Make sure you identify your base cases first and put those up first. Okay, please. Pretty please. And then you can identify the general cases and provide a solution afterwards. All right. This is what we talked about earlier. Which do you use? It depends on the problem. This is where you need to come in and decide which way is better. Should you do it iteratively or should you do it recursively? For this class and for most of your programming, you want to do it the way you really want to do it with the fewest amount of code that is still very readable. Sometimes that's recursive, sometimes it's iterative. Although take a guess at which one it ends up usually being. I found this might be something that. So far, what type of solutions have you been doing? Loops, or the iterative solution. It turns out, from my experience, most of the problems I solve, the iterative solution is an easier way to read the problem. But there are a significant number, I'm not going to say 40%, probably around 10 to 15 or 20%, that are just way, way easier if you just do recursion. And we're actually going to go through a good number of those in this course. Yeah, as I told you, when you call a function, it allocates new memory on the stack. So that does, one thing to keep in mind is that does mean that a recursive solution in general will consume more memory space and computer time, because the computer has to, whenever you call a function, there's computer cost of setting up that new function call and allocating the memory. So there is a little extra cost to doing a recursive function. That just keep that in mind if you ever have performance issues. But in this course, your performance issues are going to be more based on big O, not whether you're doing an iterative solution or a recursive solution. Especially today, the overhead of recursive function call is not noticeable. I would go so far to say that except in extreme circumstances, it is negligible. You shouldn't have to worry about it. But do be aware of it. Yeah, whichever solution is more obvious, please go with that one. All right. Well, that was about it. Would you like another example of recursion? Or you want to go straight into
I'd like
another example? Did we do the maze in your previous class?
Yeah.
And did we do that one recursively?
No.
You don't remember? Let's do a maze one. Maze is a good classic recursive problem. And it's not tail recursion, which is even better. Let me stop.